Pues nada, ya hemos hecho nuestra primera pausa de café, nuestro primer descanso, y vamos a empezar la segunda sesión del día de hoy, del viernes, con Flexoptix, con Gerhard, Stein y Thomas Meibel.
Thomas Weibel no está aquí con nosotros.
Vale, pues, Gerhard.
Él está en otra NOC,
Vale.
así que nos
Bueno, nos van a hablar de transceptores, que es un tema que creo que a todos nos interesa bastante, o sea que cuando quieras.
Vale, entonces voy a iniciar. Una cosa que quizás decepcionaría o decepciona, no estoy seguro. Esto va a ser en inglés, para que todos me entiendan, pero pueden preguntar en español, inglés, alemán. Sirve los tres idiomas, no hay problema. Entonces, let's start. Let's start with coherent transceivers and why you want to have them and why you need them and why they're important. This presentation is split in two people. As you already mentioned, Thomas Weibel is the founder and owner of this company. I'm here for him and giving this presentation. We built it both. It's split in two parts. We have first the theoretical part, which means we have some mathematics here, hard mathematics, so be aware, but since you had your coffee and your Coke, you can perfectly listen and understand it. It's like a roller coaster, and when we are on the top of the roller coaster, we go down to the practical part. Yeah?
Try to leave the speaker a little slow, because you are very fast.
Little slow. Okay, I will slow down. My apologies, I do my best. So let's start. Yesterday I was asking you about form factors. Here's a small summary of them, CFP. C, by the way, stands for CN or CentOS or something like that, from Latin, nothing to do with CentOS, which is a Linux distribution. It's 100G, and these form factors are quite interesting. We still support it with some devices. These are these bigger connectors that are being used. They have been evolved over the years. CFP2 is a little bit smaller, and Cisco also had the idea to put that CPAC in between. That wasn't that quite popular, but yeah, quite a challenge. And with the CFP, we had the situation that you could have had a transponder card like this with a DSP of manufacturing technology of 28 nanometers. That was many years ago. But since we have been advancing with manufacturing technology, now we are on 7 nanometers. And you know, with the processors, we are going even down to 20 nanometers. And after that, we have most likely angstrom, and you have like 20 atoms to put together to describe one via in your semiconductors anyway. They've been more efficient, and it can be small, like really a plug, as you can see on our Flexbox. We can put it there. And what is this DSP? The digital signal processor has a little bit of intelligence, I'd say, where you can calculate different things. And what these are things is all the theory about here. But first of all, let's talk about the theory of a normal transceiver, a non-coherent transceiver, or we also call it direct detection transceiver, and its limits. With light, it's easy. If you want to build a transceiver, you just take an LED on one side, put your fiber, on the other side you have a photodiode, and that's it. If you want to have a certain bandwidth, you do it with some frequency. You push in some bits, like 10, 10, 10. That is what you want to push in, what you calculate, your binary data, but usually when you measure it, you have like, because nature doesn't behave like that, so what you end up measuring are curves that can be described by a model like the sinus curve, cosinus curve. Choose one of these, doesn't matter. What is the problem? Well, when you start measuring this and taking values, you have a certain margin, right? For 1, you have the signal of 1, and for 0, you have the signal of -1. But what happens if you increase the bandwidth, which you can do by increasing the frequency? Well, you end up measuring curves like this, and the problem is, well, okay, I'm faster, awesome, but I have to reduce my margin. Now I'm not saying 1 to 1, I'm matching my 0 to 0. Okay, fine, easy to calculate. But what if I go even faster? It becomes harder and harder to really see the difference between what is 1 and what is 0, because the margin is getting closer. And that's really a big challenge with the transceivers, because you have noise and all that, and yeah, that is something you want to avoid. Well, it turns out using light and just saying, hey, I'm putting some signals, lighting up and have a photodiode, it's a little bit too simple. Light has way more properties you can consider. And one of the properties is polarization, and that is what our coherent transceiver is doing. So it's a new approach where we look at more properties of the light. So we already have amplitude, and with higher bandwidth transceivers, usually we have several amplitude. The previous slide was very simple, but usually you have 4 amplitudes. But now we are adding more properties, 2 properties, phase and polarization. Talking about polarization, who of you has a protective screen? So your neighbor cannot look. That's one of the principles. So you can hide light, you can extend it, and like we engineers say, we can invert a problem. Instead of protecting the light or filtering it, we're extending it. We have a laser, we give coherent light, and we mix it. And that's the idea. Because when you mix it, you have your cable. Like imagine this is your C-axis, the line, where you're putting your optical. This is your signal. Doesn't look like a sinus signal because we have the second property of phase. I get this into next slides, but just imagine it's a combination of sinus, wave, phase shifted. But what you can see is we have our X-plane like this, if you look from that side on your line, and now we can rotate it like that, and you see a different sinus signal. What does this mean? This section is your window, and in this section you can put more information if you really use a property of polarization. You can double your bandwidth already. So we already doubled it with that small trick, basically. Yeah, and if we look at our cut fiber, it looks like this. No human can really decode this. It's like a hello world message we are transferring. This was a simulation, basically. And now you have a device, your DSP, that needs to understand the signal. So you send it through your laser, looks like this. On the other side, you have your decoder with a local oscillator. It has to decode it. Is the speed all right? Or shall I slow? Okay. Yeah. Another interesting aspect is the eye diagram. I try to explain it the best that you say, if you have an oscilloscope and you're measuring the signal, and you never refresh your screen, you end up seeing the eye diagram by. You're drawing all these lines. There are sinus curves where it's doing the transition between 1 and 0, no? Downwards, upwards, on this side, or you keep the signals the same. Why we are doing that and why aren't we never refreshing the screen? Well, the idea is to see the signal quality. You are pushing a lot of bits, it's very fast, your eye cannot follow it, but if you print it on the same screen with your moving window and you never refresh it, you never delete it, you end up seeing something like that, and if you see signals in between or the eye is closed, something like that, you know that the quality of your fiber or your transceiver is not good. So that is why we use the eye diagram. That really helps us on measuring signal quality. Yeah, and now comes the harder part, the mathematical part. Complex numbers, imaginary numbers. This is a complex plane. The in-phase component is a real part, you have heard of it, and the quadrature component is imaginary part. These are direct detect transceiver. OK is on-off keying, so we have 1, 0, 1, 0, and we are just here on this line putting our signals. There's no complex part. Now we are changing this up, not yet with this one. It's a PM4, what I already explained, different amplitudes. If you want to increase the bandwidth by 2, you make 4 different levels of amplitude, and yeah, that's it. Coherent. Let's get to the coherent. This is more interesting. Now we are using phase shift, what I was spoiling before. With phase shift, you are saying, okay, I'm pushing my sinus signal, but I'm phase shifting it as well, and I put several on it, and I can properly detect it with my device I have. The DSP is smarter, can do more things. So we are drawing a diagram like that, and all my points are going into my complex diagrams. I don't have amplitudes which do not have imaginary parts. There's always only real part. There's a mixture of them, and what you try to do is keep this grid of same distance, this equilateral, basically. Yeah. maybe another example to explain imaginary numbers. It's a rotary disk, so if you want to measure some optical signal that is going through this header here, which is, it's just basically shooting down light, and on the other side you have a photodiode, and you detect it, and you measure a certain frequency. What can you measure with this device? What do you think you can measure? It's quite... Any ideas? It's basically a rotary disk. You measure a rotational speed, nothing else. So what you're doing here is mechanical rotation converted to a frequency of light, and that's it. The more interesting question is, why do we need a second header with an imaginary part? Why do you think a second one makes sense? Any idea? We are measuring rotary speed. Why do we need a second header if we already have speed? Why do you think? What is the other information we are still missing? Huh? Yeah, direction, yeah, that's correct. Because if you check at our diagrams, depending into what direction they move, you can recognize a certain pattern. If you change the direction, you have no idea with only the real part into what direction it's rotating. But with imaginary part, you just watch the pattern and you find it out. You know, is it clockwise or counterclockwise? Thank you. All right. Another interesting value more on the electrical communication side is SNR, signal to noise quality. It's a comparison in your diagram. Now we are looking at the time again between our signal that is used for us and the noise we want to avoid. We always have noise. We cannot fully get rid of it. But the distance between it is what really matters. And we measure it in decibel, which is useful because you can just add it. It's logarithmic, basically. And yeah, when we usually talk about SNR, we have two kinds of SNR, the electrical part, which is the interface, and the optical part on the other side where your fiber is connected, OSNR. So these are the terms we usually use. Another term to watch is interesting when you have your complex planes I already explained. To give you an example of signal to noise ratio, a value between 30 and 20 is good. If it gets down, it's harder to find out whether it's noise or really signal. So obviously you have something like that. You cannot redetect what bits were transferred. So you want something like that, you put a grid on it, and you can still move in your margin. And if you see the dots are not so well aligned, but you still can reconstruct them. But if your signal-to-noise ratio becomes worse, then it does not work anymore. Right, that was the theory. I hope it wasn't too much. Let's get to the practical part. We work together with DSX, and with our coherent transceiver, we set up a Nokia switch. And questions later, please? Yes? Oh, okay. And special thanks to Daniel Melzer. He helped us out on this Nokia gear to get it arranged and all this. Can be complicated sometimes. And we looked in our SROS console and how it reacts to the transceiver, and we're looking at some numbers. This is nothing special. It's a tunable transceiver. It sets up its frequencies in which range it moves in order to bring the link up. It has different grids that are supported. This is nothing special, nothing to do with the coherent. But one aspect that is interesting, you can read it from every transceiver usually, is the temperature. The temperature is something you have to observe. You really have to look forward to your alarm and high and low warning. Also not so special, but very important for one thing, because the coherent transceiver has this challenge. Optical light is 1 milliwatts, it goes out, more or less, depending what transceiver, but most of the wattage you are putting into this transceiver is dissipated in heat. It's like a processor. You have to cool it down, even more than direct detection transceiver. So you have to look forward for this. This is a good temperature still, but yeah, that is what happens. More interesting are the coherent parameters we discovered the switch gave us. What you have to configure is not just the TX channel, you also have to configure the IX channel so they match perfectly. The DSP really needs that in order to see there's a matching, because it could be confused, so that is something you have to do. Then we have the sweep part that is interesting. You can also configure it in automatic mode. It calculates which 3 parts are appropriate per nanometer. You can put in manual and configure it yourself. You also have your alarms if the value is not good, because you also have the challenge with chromatic dispersion. There's a margin it puts and can also warn you about it. Another interesting parameter is the difference in group delay, which is basically when you have these two planes. I was talking about this cable and the section. We cut down and we saw in 3 dimensions these two planes you were seeing. There could be a time shift between them. You want to avoid this, but it can happen. So there's also certain tolerance for your DSP to recover it properly. And yeah, you can also see this parameter, it gets detected. More coherent parameters are the RxQ margin, which is really the Q factor we found in our specifications, which is a value where you can move in your margin before the FAC cannot correct your errors anymore. So low value might be good, but at a certain point, yeah, it gets weird. With the OSNR, optical signal-to-noise ratio, optical part, polar, we also have 2 values. They should be equal. I don't know what the effect exactly is if they are different. It could be some strange material in your fiber. You shouldn't have that. Maybe there's another effect, but it still gets recorded, and if the values are too different, you should maybe change the cable or look at your attenuators or whatever you have in your connection. Maybe some amplifier does something differently, but yeah, that is something you should also look over. They should be equal. Compatibility is interesting. The ZR transceiver with support has different application modes, and it also was interesting to observe on the Nokia SROS switch what it detected. It detected OpenZR plus OFAC, which is this code, but we do not support this code. There are different codes. You can also use a 400G transceiver and split it up into 4 times 100, and on the other side, you have 4 transceivers that are receiving with these bandwidths. This is something you can do, but you have to configure it, and application codes can help you on that. And OpenZR Plus was interesting that it detected that one, because if you look further, we have an optical compliance here that also was detected, and it really is for that code. So which one did it really apply? We looked at APROM, was really that one. So there's sometimes confusion, and something you have to look forward. I'd say the message is keep your operating systems up to date. They're still developing and detecting these transceivers properly. Very important. Right. Yeah. Anything else about OpenZR and OIF? Yeah, different tolerances that you can drive on. This one is the most dangerous one. Anyone has an idea how many milliwatts we are transferring if we have 0 dBm? Or any idea what dBm means? Yeah? It's what? What? It's what? Yes. It's really milliwatt. 0 dBm, you multiply it, it's 10 power to 0, which is 1. So this here is exactly 1 milliwatt. And these values are way lower. Yeah? dBm is to your logarithmic scale. This is a high power one. With this one, you have to be careful when you connect it. Laser is more powerful, but you can also destroy the other parts of photodiodes. You have to look at your gears. These can be a little bit dangerous. Yeah, like another takeaway. Yeah, and what else? We also announced a little bit of future we have been observing, and what are the steps to increase bandwidth. I already mentioned that we can increase the frequency. This is this axis, the baud rate. We can increase this and get higher bandwidth. I already talked about the challenges, how to detect the signal becomes difficult, but you can do more with light. DP is dual polarization, what I was talking about, the planes. So if you do that, you can upscale your transceiver by 8 times, and if you do your math in your head, yeah, I mean, it's really a good jump, and it's still very efficient. Finally, we are really getting out everything of our light, all the properties that are possible. It's a little bit more than an electrical signal. That is one thing you can do. So you have these two directions, how you can go, but what really will be in the future, we have to see. Phase shifting, 16 QAM is a diagram I showed, 16 points. You can increase it. We have seen it with Wi-Fi. Wi-Fi also uses that QAM diagram. It's usually 1024 or 248, something like that, Wi-Fi 7, not sure. You have even more points in your complex plane. So that's something that also could happen, can happen. We have to see what the future will bring us. But we have 800G, 1.6 terabit is currently in development, and 3.2 is still on a paper. But I think, I don't know, 26, 28, it might be a product. We have to see. I mean, there are still these cooling challenges, manufacturing technology. We have to see what will happen. Anyhow, that's our company. That's what we do, what we are. Thank you very much. And I'm open for questions. And feel free to ask me in any language I can service you. Thank you.
Thank you very much, Gerhard. Thank you for trying to slow down because you're all here.
My pleasure.
No problem. ¿Alguna pregunta para Gerhard? ¿Todo clarísimo? ¿No hay preguntas? Pues si no hay preguntas...
Todo está claro.
Un momento.
Me pueden preguntar después. Todo bien. Vale.